Hello everyone. Before diving into today's topic, we want to take a moment to thank you for your support. Every like, comment, and subscription truly makes a difference and helps this channel grow. If you enjoy our content and don't want to miss the next videos, subscribe to the channel and turn on the notification bell to receive all updates. In the darkness that followed the Big Bang, for hundreds of millions of years, the universe was an opaque ocean of neutral hydrogen, devoid of stars, galaxies, and visible light. It was the Dark Age, that enigmatic period that preceded the ignition of the first luminous sources. And it is precisely there, in that cosmic night, that the roots of the primordial galaxies lie, the ancient agglomerates of matter that would give rise to the structured universe we know today. Thanks to the most recent observations, conducted especially by the James Webb Space Telescope, JWST, we can finally extend our gaze beyond the theoretical limits of our imagination, venturing into an ever more remote cosmic past, where time flowed with a density we can now only attempt to reconstruct. Launched in 2021, JWST was designed to probe the deep universe. Operating primarily in the infrared, it is capable of detecting the light of objects so distant that their original emission has been stretched, redshifted, by the very fabric of spacetime, which has been expanding for over 13 billion years. This means that every image returned by Webb does not show what the galaxies look like, but rather what they looked like when their light was emitted. A true journey through time, which has now broken record after record. One of the most extraordinary discoveries so far is that of the galaxy MOM Z14, whose light comes from a time just 280 million years after the Big Bang. Its estimated redshift is greater than Z approximately equals 14, placing it within the era of reionization, that critical period when the first stars and galaxies began to ionize the surrounding gas, making the universe transparent to light. MOM Z14 is small, with an estimated mass around 10 to the power of 8-10 to the power of 9 solar masses, but it already contains heavy chemical elements: carbon, oxygen, nitrogen. These elements, as is known, are produced inside stars. Their presence implies that a previous generation of stars had already lived and died, releasing metals into the galactic environment. This drastically narrows the time frame for structure formation. It means that star formation may have begun perhaps less than 100 million years after the Big Bang. If MOM Z14 represents the chemical spark of complexity, the galaxy Zhulong, observed at a redshift of about Z approximately equals 5.2, corresponding to over 12.3 billion years ago, is perhaps the most visually unsettling discovery. It is, in fact, a spiral galaxy, with well-developed arms, coherent rotation, and a mass of about 10 to the power of 11 solar masses, comparable to that of the present-day Milky Way. This structure, according to canonical theories, should not have been able to form so quickly. Cosmological simulations, such as Illustrious TNG and Eagle, suggested that spiral galaxies require at least 6 to 8 billion years to develop orderly arms and stable disks. Zhulong, however, already displays them, with a dynamic balance that is surprising for a universe still dominated by turbulence at the time. These observations have triggered an earthquake in the astrophysical community. An increasing number of high redshift galaxies, Z greater than 10, have been identified in narrow areas of the sky such as the CEERS field, Cosmic Evolution Early Release Science, and JADES, JWST Advanced Deep Extragalactic Survey. Some of them appear to have stellar masses between 10 to the power of 9 and 10 to the power of 10 solar masses, forming stars at rates comparable to those of local starburst galaxies, up to 500 solar masses per year. Formation rates unsustainable for standard models. The question naturally arises: how could the universe have produced so much structure so early? One hypothesis is that the initial seeds of galaxies, density fluctuations, were more pronounced than predicted by the cosmic microwave background. Alternatively, dark matter may have a more interactive or warmer nature than assumed. There are also models that hypothesize the existence of primordial black holes, formed directly from the collapse of quantum density fluctuations in the very earliest moments of the universe, Z greater than 30, which would have acted as gravitational nuclei for early galaxy formation. Some of these black holes might still survive today as supermassive black holes at the centers of ancient galaxies, such as that of GN's 11, one of the brightest and most distant objects ever observed, Z approximately equals 11. But the implications go beyond astrophysics. The fact that many of these ancient galaxies show a richness of metals and dust suggests that the ingredients of life, carbon, oxygen, silicon, iron, were already widespread in some regions of the universe less than a billion years after the Big Bang. If rocky planets and organic molecules are tied to the presence of these elements, then it is plausible that potentially habitable environments existed much earlier than previously believed. This possibility opens up a dizzying reflection. Life, or at least the potential for it, might be almost as ancient as the universe itself. And if so, the question, are we alone, takes on even greater weight. Primordial galaxies also serve as tools to measure the universe's expansion. Discrepancies between the value of the Hubble constant calculated from the cosmic microwave background, Planck, 67.4 km per second, MPC, and that measured from supernovae, SH0ES, 73.3 km per second, MPC, the so-called Hubble tension, might find answers precisely in the study of the most distant galaxies. Knowing the star formation rate, mass distribution, and amount of ionized gas helps us better constrain fundamental cosmological parameters, including the nature of dark energy, which today makes up 69% of the universe but remains an almost total mystery. Beyond the science, however, remains the wonder. Looking at these galaxies means looking at the foundations of reality itself. Every image JWST gives us is a temporal paradox. Light that traveled for over 13 billion years, now striking our sensors, telling us a story long concluded but only now observable. It is an act of cosmic archaeology, an evocation of a past we cannot touch, but we can understand. In them, our origin is reflected. The atoms of our bodies come from those first stars that exploded in silence, in galaxies now dissolved or transformed. In conclusion, the most ancient galaxies and the new structures we discover today are not mere astronomical curiosities. They are sacred texts written in the language of light, archives of a past that is also our own. Every data point collected, every spectrum analyzed, every rotation curve calculated is a step toward the great cosmic understanding, that deep yearning that has driven humankind since the first time we looked up at the sky. And today, finally, we can look out there and whisper, I remember you, universe. And in remembering you, I recognize myself.